Have you ever tried sending a software update from Earth to a spacecraft 15 billion miles away? No, this isn't a scene from a sci-fi movie. This is a real challenge faced by NASA in maintaining one of humanity's most iconic missions, the Voyager space probes. In a cosmic game of patience and precision, engineers had to reprogram half-century-old computers, still chugging along in the cold silence of interstellar space. And the most fascinating part? These ancient machines have just 70 kilobytes of memory. That's smaller than a single photo on your phone. Yet, they continue to function beyond expectations. So how do you fix a 50-year-old computer from billions of miles away? Let's dive into this remarkable tale of ingenuity, nostalgia, and cutting-edge engineering. Back in 2015, NASA posted a rather strange job listing. They weren't looking for someone to write in Python or JavaScript. Instead, the ad asked for someone fluent in Fortran and assembly, languages that most modern-day coders have only read about in textbooks. These languages were widely used in the 1940s and 1950s. The job? To help support the tiny specialized team responsible for the Voyager probes. That's right, Voyager 1 and Voyager 2, launched in 1977, still operate on their original hardware, complete with those long-retired programming languages. No upgrades. No new systems. Just reliable, old-school tech that somehow continues to function despite decades of deep space radiation and wear. Each Voyager is powered by a set of 3 main computers. They're ancient by today's standards with memory limitations that would seem laughable now. But that small amount of storage, just 70 kilobytes, is exactly what's kept these machines alive and running for more than 4 decades. Voyager's main computer monitors the spacecraft's systems and health. Another handles the spacecraft's orientation, using stars as reference points to keep its antenna locked on Earth. The third manages data collection and storage from the scientific instruments on board. Together, this trio has successfully guided both probes on journeys through the solar system, past planets, and into interstellar space. But unsurprisingly, things don't always go smoothly. Just last year, NASA scientists noticed that Voyager 1 was sending back corrupted telemetry data. The probe's position and orientation information, the very data that lets Earth know where Voyager is and where it's pointing, had become scrambled. That was a huge problem. If Voyager can't keep its high-gain antenna aligned toward Earth, we lose communication. And at 15 billion miles away, losing contact means losing one of the last messengers from the early space age. So the team had to act fast. But fast is relative when every command takes over 22 hours to reach its destination, and another 22 hours for a reply. To make things worse, Voyager's thrusters, the tiny rocket engines responsible for adjusting its orientation, were starting to fail. These thrusters work by spraying small bursts of hydrazine, a chemical propellant. But after decades of use, leftover hydrazine residue had begun clogging the fuel lines. Voyager is already using its backup thrusters, and if those become unusable, it could mean the end of the mission. But with no way to physically clean or repair the spacecraft, NASA had to come up with a workaround. One involving a carefully crafted software patch that could slow down the fuel buildup and restore its orientation functions. Now, imagine writing a software patch not for a modern laptop or server, but for a computer that predates Windows, the internet, and even personal computers themselves. That's exactly what NASA's Voyager team had to do. They couldn't just plug in a USB and upload the fix. Instead, they wrote lines of code in assembly, optimized for the spacecraft's extremely limited memory. And then, they had to test and simulate every line of code on Earth, using ancient replicas and emulators of the Voyager system, to make absolutely sure nothing would go wrong. But this wasn't the first time NASA had to get creative with Voyager's software. When Voyager passed Neptune in the late 1980s, engineers faced a unique challenge. The light near Neptune was nearly 900 times dimmer than it is on Earth. To take usable pictures, the team had to reprogram the onboard cameras to allow for longer exposure times, essentially giving the cameras more time to absorb the faint light. That required sending a custom software patch across the solar system. And it worked perfectly. Once the Neptune flyby ended, NASA began shutting down unnecessary systems, like the cameras and some scientific instruments, to conserve power. But all those systems still had code stored in the limited onboard memory. That was wasted space. So engineers performed a complete software overhaul. They rewrote the code, removed support for deactivated systems, and made room for other essential processes. That's the same strategy they're using now, to rewrite, repurpose, and reinvigorate a 50-year-old system to keep it going just a little longer. Still, one big question remains: how exactly do you update something from 15 billion miles away? The process is both beautiful and nerve-wracking. First, NASA writes the code on Earth and simulates it on replica systems that mimic Voyager's onboard computers. Then, once they're absolutely confident, they transmit the software via the Deep Space Network, a global system of massive satellite dishes designed to communicate with faraway spacecraft. It takes nearly a full day for a command to make the round trip from Earth to Voyager and back. So if something goes wrong, the team can't just Control+Z the error. Every transmission must be perfect. And that brings us to the present day. Despite its age, Voyager is still receiving updates, still collecting data, and still holding onto a tenuous line of communication with Earth. It doesn't have an operating system. There's no user interface. Every command is raw, every update is handcrafted. And yet, this machine, designed in the 1970s and launched with just a cassette tape worth of memory, is still doing science in the deepest regions of space. Think about that. We live in a world where phones get outdated in 2 years. But Voyager has been pushing the boundaries of space for nearly 5 decades. All because a group of brilliant, persistent engineers keep finding ways to talk to it, teach it, and update it, even from 15 billion miles away. And this story isn't over yet. The next part of our journey explores how the engineers protect Voyager's fragile data, manage its last remaining power, and what it means for the future of deep space missions. Stay with us because what's coming next will blow your mind. Imagine sending an update to a spacecraft so far away that even light takes nearly a full day to reach it. That's exactly what NASA has been doing with Voyager, communicating with a machine that's now drifting through interstellar space 15 billion miles from Earth. But updating Voyager's software isn't as simple as plugging in a USB and hitting upload. It requires a deep understanding of its hardware, its memory system, and the language it speaks. And at the heart of this update is one of the most remarkable pieces of technology, Voyager's memory. It's not like modern RAM or solid-state drives. Voyager stores its instructions using something called plated wire memory. It's a type of non-volatile storage that doesn't rely on electricity to retain data, meaning it can keep information even if the power cuts out, a perfect design for a spacecraft that might go dark at any moment. Plated wire memory is essentially a three-dimensional grid. Thin wires crisscross and pass through small metal plates. Each crossing point represents a bit of data, either a 1 or a 0. Now imagine a bit like a tiny magnetic switch. When a current is passed in one direction through a specific wire and plate, it aligns the magnetic field in a certain way, that's a 0. Reverse the current and it flips the magnetic field the other way, that's a 1. This means engineers can physically change bits in memory by sending currents through wires. Each tiny change is carefully planned and executed, bit by bit. This design has stood the test of time. Even without power, these bits retain their state, allowing Voyager to wake up and continue operations after long periods of silence or low energy. But memory on Voyager is incredibly limited, just 70 kilobytes spread across all 3 onboard computers. That's smaller than the size of a single web page today. Because of this constraint, the team at NASA had to be extremely efficient in the way they wrote Voyager's software. Every line of code, every instruction had to serve a purpose. They couldn't afford to waste space on unnecessary commands or bloated code. To handle repetitive tasks efficiently, engineers developed what's called pseudo code. Think of it like shorthand commands, simplified instructions that trigger more complex sequences when read by the onboard interpreter. Instead of writing the full instruction every time, Voyager systems could just call one of these shortcuts, saving both time and space. It's like setting up macros on a computer keyboard, but way more advanced and built for space travel. Now here's the catch. No human can code directly in binary. The ones and zeros that the spacecraft understands must first be written in a higher-level language that humans can manage. For Voyager, that language is assembly, with some parts written in Fortran. Assembly is just one step above binary, allowing coders to write instructions in symbolic code that can later be translated or compiled into machine code. Once compiled, the code is ready to be sent to Voyager. But this process isn't fast. Not even close. Updates are transmitted using NASA's Deep Space Network, a global system of giant satellite dishes that communicate with far-off spacecraft. At Voyager's distance, data travels at just 16 bits per second, barely enough to send a sentence every minute. And then, it takes nearly 22 hours for that signal to reach the probe. That means any mistake in the code can take days to fix, and even small updates require extreme precision. What makes this process even more impressive is how the updates are received and processed by Voyager itself. The spacecraft's computers are what's called interrupt-driven. This means they run a list of ongoing tasks until they receive an interrupt signal. That interrupt tells the computer, "Stop what you're doing, this is more important." When NASA sends an update, it includes this interrupt signal. Once Voyager receives it, the main computer pauses all normal activity and shifts focus to executing the new instructions. It then begins flipping the bits in its memory grid one by one, aligning each wire and plate to represent the new code. After the update is written, a verification check runs to make sure everything was received correctly. Only then does Voyager resume its normal operations, now running with brand new software written from Earth and delivered across billions of miles. This system has proven surprisingly resilient. Over the decades, Voyager has received dozens of patches and updates, each designed to fix or improve its capabilities. One major update came in 1995, long after Voyager had passed Neptune. Engineers wrote a subroutine that allowed the probe to detect if certain components had failed and automatically restart them. 2 decades later, in 2014, that same bit of code saved Voyager 1. A hardware issue emerged and the spacecraft began to misbehave. Thanks to the automatic restart routine, it recovered and continued transmitting data, a digital resurrection that would have been impossible without that 20-year-old patch. And it's not just major hardware problems that threaten the mission. Even a single bit flipping in memory can throw everything off. That happened in 2010. Somewhere in Voyager's computer, a 0 flipped to a 1. That tiny glitch caused the entire system to fall out of sync. Commands started executing 2.5 hours later than expected. But NASA's engineers, now well-versed in Voyager's quirks, tracked down the faulty bit and sent an update to flip it back. Just like that, the probe was back on track. These moments highlight just how delicate this system is, and how amazing it is that it still works. Voyager's computers, its memory, and the software driving it were built in the 1970s, yet they continue to function in a hostile environment where the temperature is near absolute zero, cosmic radiation is constant, and no human hand can ever touch them again. What's even more astonishing is that all of this is being done by a small, aging team at NASA. Many of the original engineers who worked on Voyager have retired. The people maintaining the system today often had to learn Fortran and assembly specifically for this task, languages rarely taught in schools anymore. Yet this handful of experts continues to guide Voyager through the void, applying software updates and fixes like cosmic doctors treating a 50-year-old patient with no margin for error. And it's not just about prolonging the mission, it's about preserving history. Voyager is carrying the golden record, a time capsule meant for any intelligent life that might one day encounter the spacecraft. It's also still sending back data from interstellar space, offering scientists their first look into what lies beyond our solar system. Even now, as the signal grows fainter and the spacecraft drifts farther, Voyager continues to operate, because of these updates. It's one of the most impressive long-distance software maintenance projects in human history. Every line of code, every flipped bit, and every signal beamed through space is a testament to human ingenuity and persistence. With each update, NASA proves that even something launched nearly half a century ago can still teach us something new as long as we don't give up on it. And so, Voyager sails on, powered by 70 kilobytes plated wire memory, and the dedication of a team determined to keep listening for its voice from the stars.